Borobudur is a highly calibrated hydrological machine designed to withstand 12 centuries on the volatile volcanic plains of central Java. The monument consists of 55,000 cubic meters of interlocking andesite volcanic rock, stacked without a single drop of mortar. By the laws of geotechnics, an unmortared structure of this sheer mass, subjected to endless cycles of tropical rain, should have collapsed centuries ago. This 3D wireframe reveals the invisible architecture keeping the monument intact. Beneath the carved terraces lies a sprawling, gravity-fed internal grid of water channels. This engineered system safely flushes millions of gallons of trapped monsoon water away from the core. Without these precise exit routes, the accumulated water weight would have dissolved the foundation from the inside out. Borobudur's survival relies entirely on fluid dynamics. To understand its longevity, we have to deconstruct its design as a masterpiece of civil engineering. Central Java experiences an extreme tropical climate. During the monsoon season, the local topography is subjected to massive, recurring water loads. This diagram shows a cross-section of a standard retaining wall. When rainwater penetrates the soil behind a solid barrier like this, it creates hydrostatic pressure. As water pools in the void spaces, it exerts tremendous lateral forces against the back of the stone blocks. With no means of escape, the compounding weight pushes the stones outward. The wall's equilibrium is compromised, resulting in severe structural tilting. The terminal stage of this process is soil liquefaction. The saturated ground beneath the foundation effectively turns to liquid, triggering a catastrophic collapse of the entire structure. Over 12 centuries, Borobudur has suffered visible external damage and minor subsidence, but it has completely avoided this kind of terminal structural failure. It defies these geotechnical laws because the solution lies not in its solid mass, but in the highly engineered voids and pathways hidden within it. The entire complex is constructed from andesite. At a microscopic level, this volcanic rock is highly porous, defined by a deep cellular matrix. The monument is designed to act as a giant mechanical filter. Its 9th century architects utilized the rock's natural porosity to move water through the structure. To assemble the temple, builders carved precise interlocking joints into the volcanic blocks, deliberately omitting mortar. This dry-jointed construction gave the massive structure necessary flexibility, while allowing water to permeate easily between the seams of the stones. Once water enters the structure, it hits the horizontal terraces, which were cut with specific, intentional slope gradients. These subtle slopes weaponize gravity, constantly pulling the internal runoff away from the vulnerable core foundations and out toward the exterior walls. By embracing porosity rather than fighting it, the builders prevented localized water pooling and entirely eliminated the threat of hydrostatic pressure buildup. This diagram shows a 3D model of the temple, combined with ground-penetrating radar data, revealing an extensive plumbing layout hidden beneath the stone panels. A complex network of conduits captures rainfall at the upper central dome, routing it meticulously down through the square terraces. This grid terminates at specific exit nodes along the edges, ornate stone gargoyles known as makaras. While they appear purely decorative, these makaras act as critical pressure release valves, expelling the internal fluid volume out into the open air. To keep this system functional over centuries, the conduits feature sophisticated anti-clogging mechanics. Engineers carefully calibrated the hidden pipe slope angles to generate specific water flow velocities. If water moved too slowly, volcanic ash would settle inside the stone matrix. Instead, the velocity is tuned to continuously flush sediment out, preventing fatal blockages. The internal architecture functions as an active, self-cleaning plumbing system, utilizing precise fluid dynamics to maintain its own structural integrity. This cross-sectional diagram of the 9th century base reveals a sequence of permeable layers, large stone packing positioned over fine sand filtration beds. During peak monsoons, these layers act as a braking system, with the sand systematically decelerating the water's flow rate. Controlling this flow is critical. A rapid, uncontrolled surge would carve channels through the earth and erode the soil base, literally hollowing out the monument from within. Compare this structural logic to a modern civil engineering diagram for a contemporary earthfill dam. The mechanics are identical. Both rely on core stabilization, permeable barriers, and targeted pressure release to handle massive fluid loads. The 9th century construction utilized the core hydrological logic required for modern embankment stability, applying these principles to a monumental scale long before geotechnical engineering. Even with brilliant engineering, extreme climate shifts and heavy volcanic ash fallout from Mount Merapi eventually overwhelmed the ancient equilibrium, and the complex was abandoned. During the massive UNESCO restoration in the 1970s and 80s, engineers had to dismantle and completely rebuild the monument's lower foundations. They introduced modern engineering elements to assist the ancient design: hidden reinforced concrete slabs, PVC drainage pipes, and chemical epoxy were embedded directly into the base. Today, the Borobudur Conservation Office continues to monitor the site, actively addressing new drainage leaks that recently emerged on the eastern tiers. To protect the delicate relief carvings, local experts are currently dismantling sections to repair the permeable layers, patching the compromised stone with heavy lead sheets and waterproof materials. These modern interventions are working symbiotically with the ancient pathways, giving Borobudur the physical support it needs to continue its 1,200-year battle against the water. The massive spiritual journey of the monument's terraces relies on a hidden masterpiece of environmental engineering. The structural systems functioning beneath the stone remain invisible to the pilgrims who walk the terraces, managing the environment without ever interrupting the ritual path. To continue decoding the scientific realities hidden beneath history's greatest structures, subscribe to TEMBODocs.